Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. So in this session, we are going to discuss about the maximum power transfer theorem. So in the maximum power transfer theorem, we need to determine the how much amount of maximum transfer to the load element that we need to determine with the help of this one. So similar to the other theorems, so there will be a statement, one statement for this theorem also. So the maximum power transfer theorem is states that in any linear bilateral circuit having the different kinds of sources, so the maximum power is transferred from the source to the load when the load resistor is equal to the source resistance. That is the statement of maximum power transfer theorem. The maximum power transfer theorem is states that in any network the maximum power is transferred from the source to the load. Maximum power transfer from the source to the load. So when the load resistance must be equals to the source resistance, or also we can say Thevenin resistance, then only the maximum power is going to transfer to the load element. So that is a statement of this maximum power transfer theorem. So then this theorem is purely applicable for any kind of circuits. So before going to apply the maximum power transfer theorem, we need to determine so for any circuit we need to determine the Thevenin's equivalent. Let us take this example. So this circuit having the different kinds of resistor. So we need to replace, or we need to reduce the whole network into the Thevenin's equivalent. That means we need to find out the VTH. So we have already gone through the Thevenin's theorem. So for that, the same procedure we need to follow to get the Thevenin's equivalent and also for this network. So that is we need to determine the RTH value and also the VTH value. Then after that we can apply the maximum power transfer theorem. To get the maximum power value. So same circuit we need to take. This is the Thevenin's equivalent circuit. So for the Thevenin's equivalent circuit, we need to write the current value. So here IL equal to, so we would like to write VTH upon, according to Ohm's law, VTH upon RTH plus RL. So this is the equation number 1. So now we would like to find out the power across the load element. Power across load element. Power across the load. So that PL equal to, we need to write IL square into RL. So this is the equation number 1. Then we need to substitute equation number 1 in equation number 2. We would like to get PL, the load power value equal to the that is VTH upon RL plus RTH whole square into RL. So then we need to write in terms of others, that is a PL equal to the VTH square into RL. So divide by the RL plus RTH whole square. So this is the equation number 3. So we need to take the Thevenin's equivalent circuit. This is the VTH. Also we can treat it as this one is a VTH. So VSR, VTH also we can say. So this is internal resistance or RTH also we can say. So based on this one, we need to find out the IL value according to the Ohm's law, that we got it as the VTH upon this value, and we need to try to find out the load power value. So why should we concentrate on load power? Means if you are able to get the load power, then only we will get the maximum amount of power to the load, because the theorem is saying us. So whenever the maximum power transferred from the source to the load, when the load resistor must be equal to this value must be equal to the source resistance, then only the maximum power is transferred from the source to the load. So that's why we have derived this one. So need to determine the load power value here. The load power value equal to the VTH square into RL upon RL plus RTH square. So now I need to determine the condition for the maximum power value. How can we get the maximum power value? So for that, so we need to go for condition for maximum power value. So that is a condition for maximum power. So condition for maximum power, for that case, so we need to do the differentiate. We need to do the differentiate the equation number 3 with respect to RL. So with respect to RL, we need to do some differentiation, and then equate to 0. then only we will get the condition for maximum power. So for that, the equation number 3 is that is a PL equal to the VT square into RL divided by the RTH plus RL whole square. So that means we need to regard to the above statement, we need to do the dPL upon DRL, then we need to equate to 0. So then only we will get the condition for maximum power. So for this d by DRL of, so this value, that is VT square into RL upon RTH plus RTH whole square. So then equal to 0. So this is the whole term is looks like a U by V method. U by V method. So according to the U by V method, d by dx of, that is a U by V, which is equal to U dash into V minus V dash U upon V square, according to this formula, because the term is looks like, so here U by V method means we need to do the differentiation. So to get the condition for maximum power only, there will be a certain condition. So the certain condition is RL equal to the RTH. RL or R internal equal to the RTH. So then only we will get the maximum power across the load. So for that we need to do the differentiation for power value. So based on that one we will get like this the term. So the term is looks like a U by V method, so that we can apply the differentiation of U by V method. So similar to that case similar to that case, so we need to do the differentiation for this term, that is so here the U term is upper one, this is the U term and this is the V term. So according to the formula we can do the differentiation for this one. So we will get that is a VT square, according to the U dash, VT square into 1 we got, that is a differentiation of RL, d by DRL of RL means we will get 1, so that we keep it as a 1 here. So into, so we can write the V term as same, keep as this, that is RTH plus RL whole square, RTH plus RL whole square, and we need to keep this term is as it is. So minus, according to the formula we need to keep some minus here, so that is a here minus, then according to the formula need to do the differentiation of, so RTH plus RL whole square, so this one is RL, so that is RTH plus RL whole square, means we will get the 2 times of RTH plus RL, because differentiation of x square we will get the 2x. So similar to that we will get the, so RTH plus RL whole square is the 2 times of RTH plus RL. So that is the V dash, then into d by dt of d by DRL of, into d by DRL of, so this term, that is RTH plus RL. So this term we will get 0, this term we will get 0 because it's a constant, and then this term we will get 1. So based on that one we will get only 1. So into, we'll keep the U is as it is, that is a VT square into RL, so divide by V square. So this is the dPL upon DRL value, DRL equal to, so this one, what is the V square value, that is RTH plus RL whole square means whole to the power 4 equal to 0. So this term is going to become 0 and the remaining also we will get 0. So the value is we will get VT square is going to take common of the remaining terms in the above numerator is RTH plus RL whole square minus 2 times of RTH plus RL into VT square into RL equal to 0. This only we will, this terms only we left, so we got only these terms after the simplification, because this one is going to become 1 and this one is going to become 0 and remaining also going to become 0. So this VT square also going to send right side, will get 0, that is the final simplification term is, so that is the RTH plus RL square minus 2 times of, we need to take the VT square as common here. Yeah, that is so that there is no VT square here. So need to take the common as a VT square, then is no VT square here. So directly we need to write the RL is here, and this is the whole term. So the final term is 2 times of RTH plus RL into RL is left. Only these parameters are going to left. So the further steps we need to, this his looks like a plus b whole square. We need to expand the a plus b whole square here, and remaining terms are going to simplify, and we will get here the remaining terms are RTH square plus REL square plus 2 times of RTH into REL minus 2 times of RTH into REL minus 2 times of REL square equal to 0. So here these two are going to get cancelled. These two are going to get cancelled, and the remaining terms are left like RTH square plus REL square minus 2 times of REL square equal to 0. Then need to simplify this one. We will get the term is going to be RTH square minus REL square. So therefore RTH equal to the RL. I mean to say RL must be equate the internal or Thevenin resistance. So then only we will get the maximum power across the load. Then only we will get the maximum power across the load. So the term we will going to write like RL equal to the RTH or R internal. So then only there will be a maximum power appear across the load resistor. This is the condition for maximum power. So this is the condition for maximum power. The condition for maximum power is, so need to get the RTH or RL equal to the RTH or R source. So because the statement of theorem is going to say it like that. That is, whenever the maximum power is transferred possible from the source to the load, so then the load resistor must be equal to the source or internal or Thevenin resistance. Based on that, we got the condition for maximum power. So this above value we need to substitute in the equation number 3. So the RL equal to the RTH, RL equal to the RTH, substitute in equation number 3. So based on that, the equation number 3 is PL equal to the VT square into RL, so divided by RTH plus RL. So this is the equation number 3. So instead of RL we can substitute the RTH, or instead of RTH we can substitute the RL. Both are same, means PL equal to the VT square into RL, keep as it is. So in the denominator we will get, so RL plus RL whole square we got here, whole square. So this is the equation number 3. We have derived the equation number 3, this one based on the circuit. So for that we need to do the simplification, then we'll get the condition for maximum power. So that value we need to substitute in equation number 3 to get the maximum power value. So here the maximum power value, so we will get the P max equal to the VT square into RL, so divide by the 2 times of RL whole square. So this is the final simplified term. So then after simplification we will get the P max equal to the maximum power value equal to the, so VT square into RL, so divide by the 4 times of RL whole square we got. So these two are gets cancelled. Therefore the maximum power across the load should be equal to the P max equal to, so VT square by 4 times of RL, load resistor. So this is the value of maximum power across the load resistor. So this is about the maximum power value, and also the condition for maximum power is a RL equal to the RTH we can say, or other words source resistance we can say, or other words we can say internal resistance. So all are same only. So this is the condition for maximum power. And the summary of the session is, so we need to use the maximum power for different circuits to get the maximum amount of power across the load. So that is always possible for Thevenin's equivalent circuits only. I mean to say, so any kind of circuit, we would like to apply the maximum power transfer theorem. First, we would like to determine the Thevenin's equivalent. So Thevenin's equivalent, we need to find out the Thevenin's equivalent circuits. So Thevenin's equivalent circuit. So similar to the Thevenin's theorem, we need to find out the VTH and also the RTH. Then if you are able to get the RTH value, so that is also same as the RL value. So based on that only, we need to find out the maximum power value. So this is the maximum power transfer theorem. So that's clearly saying us about the maximum power across the load resistor that should be always possible or transferred from the source to the load. When this load resistor must be equal to the source resistance, then only maximum power going to transferred. So at that time the efficiency should be 50% only. Based on the different kinds of cases, we will get the, so at that point, I mean whenever the source is delivering the maximum power to the load, at that time we will get the 50% efficiency only. So this is the summary of the entire maximum power transfer theorem. So this is the end of the session. So in the next session, we will discuss about the different numericals based on the maximum power transfer theorem. So thank you one and all for watching this video.